Hi everyone. Today we are going to discuss about some questions which are asked in IIT-JAM 2022. So I am basically solving the problem under the category of organic. So it is the part 1 video of the solution series. So let's look at the first questions. So the question was asked like the substrate given containing a ketone group and a acid group, and they converted into ketone to a methylene unit. This is called methylene unit. That means CH2, CH2, and the acid remain as such. So which reagent you are going to use to reduce a selective reduction? So that term is known as chemoselectivity. What do you mean by chemoselectivity? Like selectively reduce a particular functional group in the presence of another functional group. So here the question also based on the chemoselectivity, like the carboxylic acid group remain as such, and we are going to reduce the ketone into methylene group. So which reagent is best for that conditions? So let's analyze one by one. So this reagent is known as lithium aluminum hydride, and this one is sodium analog, that is sodium borohydride. This is called as BS3 or borane, and this combination, that is zinc amalgam, is known as Clemenson reduction. So lithium aluminum hydride is a strong reducing agent. Strong reducing agent. So it can reduce both the ketone and acid. Sodium borohydride also, no, sodium borohydride is a less reactive reducing agent as compared to lithium aluminum hydride. It can only reduce the ketone, not the acid, but it reduces ketone to alcohol, because the sodium borohydride is a nucleophilic reducing agent, that means source of hydride ion. So if your compound containing a ketone, if you add sodium borohydride into it, then the hydride minus ion will attack to the oxygen, to the carbonyl carbon. It will form a oxide ion with the counter ion sodium plus and hydrogen here. After workup, we will get a alcohol. But here the ketone is reduced to methylene. So this reagent we can't use. So 2 is eliminate and 1 is also eliminate. Why? It is a strong reducing agent. It can reduce both the ketone and the carboxylic acid into alcohol. So it can reduce ketone and acid to their corresponding alcohol. Then what about BS3? BS3 is a Lewis acid. So it can only reduce electron rich functional group. So out of two, the carboxylic acid is more electron rich functional group. So carboxylic acid and amide can reduce by BS3 only. So acid will convert it to alcohol by BS3 and amide will convert it to amine by BS3. So this also cancelled. So the remaining one is Clemenson reduction, and this is specific condition to use to reduce the ketone into methylene one. So the right answer is IV1, that is Clemmensen reduction. So in every competitive exam, you have to go by like this. You have to cancel the option and choose the best favorable condition for your questions. Next move to the next question. So the next question is basically based on hydroboration reaction. This is known as hydroboration reaction. So for that reaction, we need the general condition is borane, which is stabilized by some electron donating solvent like THA or diethyl ether. Then H2O2, that is hydrogen peroxide in basic condition. So in borane, the hydrogen is more electronegative and the boron is more electropositive. So if we have a double bond like this, then we can represent the double bond like positive charge over here and negative charge over here, because the positive charge at tertiary carbocation is more stable and negative charge at primary carbocation is more stable. So if we add BS3 into it, then the positive part will add to the negative part and negative part will add to the positive part. Then what will form? It form hydrogen here and BS2 here. And the specificity about this reaction it is syn addition. Like both the hydrogen and BS2 will come from same side. So if it is come from above the plane, it also come from above the plane. After that, when we add H2O2, that is hydrogen peroxide and sodium hydroxide, the BS2 group will converted into oxygen. Sorry, hydrogen here and oxygen here. So the resultant is, the reaction is like from alkene to the product alcohol. It seems like a anti-Markovnikov additions of water across the double bond. So this is the concept we have to apply here. But here it is given as the deuterated form of boron. Like this is the hydrogen form. If we replace hydrogen with deuterium, then this is called the deuterated form. So what will happen in the reaction? Let me clear that. So we have to add BD3 to the double bond. So what do we learn? Like BD3 we can write like D2B and D, and this boron part will add to the less sterically hindered carbon, that is which stabilize the negative charge, and D will add to the more substituted carbon. So in the substrate it gives like this. So this is the more substituted carbon and this is the less substituted carbon. So the hydrogen will add in the more substituted carbon, sorry, here it is deuterium instead of hydrogen, and the boron part will add to the less substituted carbon, and both will add syn fashion. Like if the methyl is down the plane, then they will come above the plane. If the methyl is above the plane, then they will come from down the plane. Sorry, down the plane, right? So after that we have to add H2O2 NaOH in both the substrate. Then what will form? It will form. So what happened after addition of H2O2 NaOH? The BD2 converted to hydroxide. Here it is, methyl is above the plane. So either one of is your answer. Now you have to look at your option. Here it is, in that answer it is written OH is at the more substituted carbon. So this will cancel because OH will be at your less substituted carbon according to the mechanism. In that third option they form epoxide. So this also cancelled. So 2 are remaining. Out of 2 and 4 we have to look which one is the our product. So here also OH is less technically hindered carbon or less substituted carbon. Here also less substituted carbon. Now we have to look at the stereochemistry. Both the OH and deuterium should be in same plane because they are coming in same side. Here both OH and the deuterium is same plane. So the answer will be your option 2. Here it is in different plane because deuterium mentioned in above the plane and OH mentioned is the below the plane. So this will be not your answer. So the answer is option D. So one more thing I have to explain you guys. So how that BD2 converted to OH in presence of H2O2 NaOH. Okay, you got it. What will be the product? So the product will be option 2. Now try to understand how that the boron species will converted to alcohol in presence of H2O2 NaOH. Okay, so how we can represent H2O2, that is hydrogen peroxide, and NaOH is OH minus Na plus. So OH minus is a base, it can accept a proton and it will form a peroxide anion. So the peroxide anion, the lone pair over oxygen, is donated to the empty p orbital of boron atom. So boron has the empty p orbital, it can accept a lone pair of electron and it becomes tetracoordinated and a negative charge over boron. So to get neutralized, that alkyl group will migrate at R minus ion and that OH group will leaves. Then the species becomes deuterium OR. After that, hydrolyze it, it will form your alcohol plus this species. So this is the way how that boron form of that compound will converted to alcohol in presence of your H2O2 NaOH. So the answer of that question is the second one, and these are the full mechanism. So now next move to the next question. So the next question is like your substrate is given, product also given, there is a change of the functional group aldehyde to acid, alcohol is remain as such. So what is the best condition out of these four for that conversion? So again here the term chemoselectivity comes, because to selectively oxidize to selectively oxidize the aldehyde to carboxylic acid, and OH will remain as such. So let's explain one by one all those options. Then we have to choose which one is the best one. So the first option is manganese dioxide. So manganese dioxide has some specificity. It will oxidize only the allylic and benzylic OH2 hydroxide to carbonyl compound. So what do you mean by allylic position? So this position is known as allylic carbon, and this carbon is known as phenylic carbon. So that hydroxide is more selective toward manganese oxide. And what do you mean by benzylic position? Benzylic position is this one. So this is called as benzylic carbon, and the hydroxide or OH group attached to the benzyl carbon is known as benzylic OH. So manganese dioxide have more specificity towards these two substrates. But here the OH is simple attached to a sp3 carbon, not a allylic position, not in benzylic position. So option 1 is eliminated. So now the second option. So in second option there is a combination of three reagent, and that combination is known as Swan oxidation. In Swan oxidation, what will happen? It will convert alcohol into carbonyl group. So what is the mechanism of Swan oxidation? So we can write DMSO. DMSO is dimethyl sulfoxide. This is the chemical structure of dimethyl sulfoxide. In ionic form, it exists as a O minus and positive charge over sulfur. Then the oxalyl chloride. This is the chemical structure of oxalyl chloride. So what will happen? Oxygen will attack to that carbonyl carbon. Electron move to that oxygen. Again, it comes back to the carbon and Cl leaves. Then the species. Then these species will form with a positive charge over sulfur. Now the chlorine ion will act as a nucleophile. It will attack to the sulfur. This bond will move, and it leaves as a carbon dioxide, and it moves towards like this. It moves as a carbon monoxide, and chlorine again leaves. So what will happen? It forms Cl, this ionic intermediate with loss of carbon dioxide, carbon monoxide, and Cl minus. After that, alcohol will come. It will act as a nucleophile, and it will attack to the sulfur, and chlorine will leave. Now what will form? Sorry, carbon, oxygen, then your sulfur. This. So the here the H plus and leaves. Now in the presence of base will abstract the more acidic proton. So this carbon contain the proton is more acidic. It will abstract that proton. It will form a negative charge here. Then that negative charge will abstract one of the hydrogen over here. It will abstract one of the hydrogen here. That bond will move towards oxygen, and this group will leaves. Then we will get your carbonyl compound plus what we will get? We will get dimethyl sulfide, sulfur and 2 methyl group. This is known as dimethyl sulfide. This is the mechanism of Swan oxidation. So in Swan oxidation, what will happen? So your alcohol get converted to carbonyl compound, but here what happened here? Your aldehyde get converted to acid. So these also not favorable for that transformation. So option 2 also wrong. What about option 3? Option 3 is known as aluminum. The reagent is known as aluminum tetraisopropoxide, and the reaction is known as your Opner oxidation. So what happened in Opner oxidation? Wait, let me clean this one. So in optional oxidation, what happened? Like a secondary alcohol in presence of acetone and aluminum isopropoxide, aluminum tetraisopropoxide, it will convert it to a carbonyl group, and this as a side product. So here also the alcohol is oxidizing to carbonyl group, but we got in our question like only aldehyde group is converting to carboxylic acid. So this option also wrong. So the remaining is silver dioxide. So silver dioxide is the specific reagent which is used to convert aldehyde to carboxylic acid. So this is the answer. So you have to remember what is the role of silver dioxide. Silver dioxide is a oxidizing agent and it will oxidize aldehyde to carboxylic acid only. So next move to the next question. So this type of substrate is given. So this is comes under a name reaction is known as Favorsky rearrangement. So what happened in Favorsky rearrangement? So here it is sodium methoxide. Sodium methoxide is act as a sodium plus ion and methoxide ion. So methoxide ion act as a base and nucleophile. So in Favorsky reaction it act as a base and it abstract the more acidic proton. So alpha to the carbonyl, this position is the more acidic, which is alpha to the carbonyl. So this is more acidic proton. So methoxide ion will abstract the most acidic ion and it will form a carbanion at alpha position. So there is two alpha position, one is here, one is the other side, but in that alpha position there is no proton. So it will abstract this proton only. Then what will form? A carbanion will form. After the formation of carbanion, a three-membered ring formed in Favorsky rearrangement. How it will form? It will attack to that next alpha carbon and the leaving group leaves. So it will form a three-membered ring, carbonyl group here, bromine here, and two methyl substituent here. Now the OMe, that is methoxide ion, now it acts as a nucleophile. It will attack to the carbonyl carbon and the double bond will migrate to the oxygen. Then it will form this species. OMe over here, bromine here, methyl group. Now this the electron over oxygen again come back. Now there is possibility of breaking of two bond. Either this bond will break, otherwise this bond will break. Let's it is A and it is B. So if A bond break, then what will happen? So there will be a negative charge here, then the carbon here, bromine here, and a carbonyl group here, and OMe. If B bond break, then there will be the formation of this type of intermediate. So in Favorsky rearrangement, at the end carbanion will form. So how to know which bond will break? After breaking of bond, the formed carbanion in which structure it is stable, that bond will break. Like at the end we are getting carbanion. So at that position, at what position the carbanion is stable, the bond will break in that fashion. So here the carbanion is at the tertiary carbon, but here the carbanion is primary carbon. So the carbanion stability is dependent upon hybridization. So the stability of carbanion is like primary carbon, like carbon negative charge over primary carbon is more stable, then secondary carbon, then tertiary carbon. So according to this order, this will be the favorable condition. But here there is one more factor which lead to this structure as the product, not this one. The other condition is, so when the negative charge will return to form a double bond here and bromine will leaves. Now there will be the formation of a alpha beta unsaturated compound. So this is the driving force, that is the formation of alpha beta unsaturated carbonyl compound, and leaving of bromine minus ion is the driving force to leads to form this product instead of going by this intermediate. So if there is no possibility of formation of double bond, then this will form, and in presence of that methanol proton source, it will form the product, this as a product. But here the driving force is the formation of double bond or alpha beta unsaturated carbonyl. So this will be your product in the given question. Okay, this is known as Faber's rearrangement. So next, move to the next question. So given like that compound name is given, that is 2,4-dinitrophenolbenzene. So it is 1, 2, 3, 4, 5, 6. So both the nitro group at 2 and 4 position. So the name is given in the question 2,4-dinitrophenolbenzene in presence of hydrogen. So it will form a complex which is represented as G, and the foreign complex or the 2,4-dinitrophenolbenzene we use for testing of which functional group. We have to write that thing. Like two things asked in that question only. One is what is the product will form after reaction with hydrogen, and why that 2,4-dinitrophenolbenzene is used. So what will it form? 2,4-dinitrophenolbenzene. Okay, for benzene there should be I system, right? This is 2,4-dinitrophenolbenzene. So when there is electron withdrawing group at 2 and that is in ortho and para position, what mechanism it follows? It follows addition elimination mechanism. So how addition elimination mechanism followed? See, so here it is your nitro. So hydrogen act as a nucleophile here. It will attack to that carbon containing fluorine or leaving group. Then the double bond will migrate. It is stabilized by the nitro group. So it will form NO2 edge like that, and here it is fluorine, and here NH2 plus NH2 and double bond N O minus plus. Then that electron again comes back like this, and the leaving group will leaves. Then what will be your product? The nitro again it comes into its original state, NH2 plus NH2. One of the hydrogen will leave H minus H plus. It will form NH, NH2, NO2, NO2. So this is the product of the given reaction. So this step is known as addition step, and this is known as elimination step. So the overall reaction is known as addition elimination reaction, and that here the intermediate formed is carbanion. So any group which stabilize the carbanion will accelerate the reaction, and that reactivity of or leaving group tendency of halide is like fluorine, chlorine, bromine, iodine in case of addition elimination reaction. But we know that iodine is a good leaving group as compared to fluorine. But why fluorine comes first here? Because the formed carbanion is stabilized by the minus I effect of the fluorine. That's why fluorine is a good leaving group in case of addition elimination reaction. So you have to remember why the fluorine comes first, because the formed carbanion will stabilize by the fluorine. It's due to its electronegativity. Then why this 2,4-dinitrofluorobenzene is used? It is used for identification of what? Aldehyde or ketone functional group. So if your compound contain aldehyde or ketone, you can confirm by dipping into a solution of 2,4-dinitrofluorobenzene. If your compound contain 2,4-dinitrofluorobenzene, it will show a yellow color in your yellow or like slightly orange color in your TLC plate. It will show orange color on your TLC plate. By this you can confirm like your compound contain aldehyde or ketone functional group. So those point they asked like what is the product and why it is used to, or like to use to identify which functional group. So next move to the next question. So next question is, these are the like any substrate out of these four react with malic anhydride to undergo pericycle reaction. So what happened in pericycle reaction? Like basically it is a 4+2 cycloaddition reaction. What happened in 4+2 cycloaddition reaction? 4 comes from your diene and 2 comes from your dienophile, right? So here you have to know malic anhydride is a diene or dienophile. What is the chemical structure of malic anhydride? Malic anhydride structure is this. This is known as malic anhydride. Okay. So here it contains 2 electrons. So it acts as a dienophile. And dienophile must contain, not must, if it contain electron withdrawing group, then the reactivity is more. What about diene? Diene must be a source of 4 electron, so it should contain 2 double bond. So both, this is called cis butadiene and this is called trans butadiene. So both contain 4 electron, but the cis conformation of the trans butadiene only participate in your Diels-Alder reaction. Why so? So for that you need to understand the molecular orbital diagram of the interaction of the diene and the dienophile. So the trans form get converted to cis form and take part in the Diels-Alder reaction. So we have to look out of the 4 option which is a, like it is a MCQ type, multiple answer type question, MSQ type. So like one may be the answer, or like 2 or 3 or 4 out of 4, like so many answer will be there. So we have to look which diene is more preferable for that dienophile reaction. So for that we need, what we need? We need a source of 4 electron which is in cis conformation, because trans one cannot undergo Diels-Alder reaction. So here just look at the middle benzene ring. So it contains 2 double bond which is a source of 4 electron and it is in cis configuration, right? So it can take in your Diels-Alder reaction. So I is the first option which is take part in the Diels-Alder reaction. Now what is it? It is pyrrole. So pyrrole contain 2 double bond that is source of 4 electron and it is in cis configuration. So it also take part in the dialside reaction. See here 2 double bond is there like source of 4 electron, but they are in trans configuration and they can't be interchanged to cis configuration because it is a ring system. So option 3 is not taking part in the dialside reaction. And what about, sorry, it's not pyrrole, it is furan and this is pyrrole. Sorry for the mistake. So what about pyrrole? It contain also 2 double bond, that is 4 electron source and it is on like cis configuration. Then it must take in the dialside reaction, but in this state it can't take part in the dialside reaction. So what is the reason? So the reason is like aromaticity of a compound is inversely proportional to the reactivity in dialside reaction. So you have to remember this. So this is the trend. So what is the aromaticity order? Like benzene is more aromatic, then pyridine, then your pyrrole, then your thiophene, then your furan. So this is the least aromatic. So it take part in a dialside reaction in this state only. So if you want to make the pyrrole to be active towards a dialside reaction, what we have to do? We have to reduce the electron density over the nitrogen. Then it becomes less aromatic and it can take part in the dialside reaction. For that, we have to protect that nitrogen with a acetate functional group. If we have a substrate like this, now this pyrrole ring can act as a source of 4 electron and it can take part in the dialside reaction. With the presence of this group, now the pyrrole ring becomes less aromatic. So option I and 2I is the right answer for that question. So next move to the next question. Okay, so it is also a chemical transformation. We have to convert aldehyde to ketone. So out of 4,